Hello everyone. In this video we are going to talk about the direct shear box test, which is considered one of the simplest and easiest tests that can be done on the soil to determine the shear strength parameters. Well, in this test, let's summarize the test before dealing with a solved example. In this test, you mainly have two boxes. The bottom box here or here is placed and is positioned. It's not allowed to move anywhere. It's not allowed to move horizontally. However, the upper box is allowed to move in the horizontal direction under the action of a shear force, under the action of a horizontal force. In this test, you have a dial gauge which gives the vertical displacement of the soil, and you have a proving ring giving the value of the shear force applied on the upper box. And of course you have a dial gauge measuring also the horizontal displacement of the upper box in this test. Well, the summary for this test can be given as follows. At the first step, after you have compacted your soil in the two boxes, you will apply a normal load. You will apply a normal load which will cause a normal stress on the soil. So the normal stress in the soil, which is sigma n, it's the normal load over the cross-sectional area of the soil. This stress is constant during the test. It's not increased during the test. For the one test, this value is constant, which is the normal stress. Then we can say at the first step, a constant load, a normal load is applied. In the second step, the soil is sheared horizontally by applying a horizontal force on the upper box, which is allowed to move in the horizontal direction. So the upper box will move relative to the bottom one. Then the shear force, the horizontal force, is increased up to failure. So we have here a force, a tangential force or a horizontal force, which is increased. So at failure, you can determine the tau maximum, which is the maximum shear stress on the failure plane. Tau maximum is equal to F maximum over the cross-sectional area of the soil sample. So after you have done your first test, you will have a value of sigma normal, which is the normal stress on the soil, which was constant, and you have tau maximum, the maximum shear stress obtained by the soil at which the soil fails. Then you can repeat this test at least three times to obtain three stress states. You will obtain sigma n and tau maximum three times. So you have sigma n1 and tau maximum 1 for the first test, sigma n2 and tau maximum 2 for the second test, and for the last test, sigma n3 and tau maximum 3. So to sum up, you have conducted three tests in the lab. You have three stress states for the soil tested in the lab, sigma normal and tau maximum for each test. Just bear in mind that for each test you use a different constant normal stress. For example, for your first test you can use sigma normal of 50 kilopascal. For your second test you use a sigma normal of 100 kilopascal, for example. And for the third test you can use 150 or 200 kilopascal sigma normal. So consequently, for every test of them you will obtain a different value of tau maximum, which can be written as follows: tau maximum 1, tau maximum 2, and tau maximum 3. The next step is to draw the relationship between shear stresses on the vertical axis and normal stresses on the horizontal axis. You now are going to do, or you now are going to draw the failure line or the failure envelope according to Moore-Coulomb failure approach. You have three stress states. You will plot the three stress states. The first one is sigma n1 and tau maximum 1. You will plot this point. Sigma n2 and tau maximum 2. You will plot the second stress state, which is corresponding to the second test, and you will plot the third point, or the third stress state, which is sigma n3 and tau maximum 3, and then you will draw a straight line passing through these points. This straight line is called Moore-Coulomb failure envelope. So if you have a compass and a ruler, you can just measure the value of this angle. It's equal to phi, and you can measure the value of the intercept on y-axis, which is C, or cohesion of the soil. Okay, so let's erase what we have written on the board. Now we will move to another topic, which is the main drawbacks of this test. These drawbacks are the main reason for using the triaxial test rather than the direct shear box test in the lab for the calculation of the shear sense parameters. The first drawback, or the first disadvantage of the test, is that the failure surface is already predefined. You have already predefined that a horizontal failure surface will take place here. However, in reality, this is not true. The failure surface in reality is not known, but in the direct shear box test, you have predefined the failure surface to be a horizontal one between the two boxes, the upper one and the lower one. The second drawback is that we don't have any measurements for pore water pressure if the soil is saturated clay. You don't have any measurements for the excess pore water pressure. Number 3, no simulation of the exact field conditions. The test doesn't simulate at all the field conditions where the soil in the field may be subjected to some confining stresses. Here you don't simulate the field conditions, and for non-uniform distribution of stresses and strain on the failure surface. There is no uniform distribution of stresses and strains. So now let's deal with our solved example. It's a very easy one. We have 3 tests of direct shear box done on sand for 2 states. The first state the sand was dense, and in the second state the sand was loose. For the three tests, you have applied a normal stress on the soil sample of 40 kilopascal and 80 kilopascal and 120 kilopascal. When the soil was dense, the values of maximum shear stresses obtained by the soil were 35 kilopascal, 70 kilopascal and 105 kilopascal respectively. However, when the soil was loose or in its loose condition, of course the tau maximum will be less than the obtained one in the dense condition. So 35, we have here 30. It's less than 35 because of course the shear stress obtained in the dense state must be larger than the shearing stress obtained in the loose state. So 35 became 30, 70 became 60, and 105 became 90 at the same normal stresses used for the three tests. So all we have to do is to plot the Moore-Coulomb failure envelope in order to be able to measure the value of C and phi. So for the case of dense sand, these values of sigma n and tau maximum obtained in the test, 40 and 35, this will be our first point. 80 and 70, this is the second point. 120 and 105, and this is the third and last point. You have done the test 3 times. Now you have to plot these 3 stress states. The first stress state 40 and 35, 40 and 35, this is the first point. The second point 80 and 70, so 80 and 70, this is the second point. And the third point to be plotted on your graph is 120 and 105, and this is your third point. So just draw a straight line or the best fitting line using an Excel sheet or by your hand. It will be a straight line. We already know that the soil is sand, so we expect that the C value will be 0. Yes, the straight line confirms this fact, and the intercept on y-axis was equal to 0. The value of phi, you can measure the value of phi by your compass or by taking the tan inverse of the slope of this straight line. So the slope of this straight line, it's equal to delta y over delta x. Just take any 2 points on the straight line and use this equation to measure the slope of the straight line. So if you take, for example, the points corresponding to the second and the third test, you have delta y 105 minus 70 over 120 minus 80. So tan inverse of this slope will give you the value of phi, which is equal to 41.18 degree. For the loose sand, we already have known that the shearing stress decreased when you transferred from the dense state to the loose state. So all you have to do is to plot these new stress states on the same graph or on a new graph paper. You have 3 points. The first point 40 and 30, this is the first point. The second point 80 and 60, this is your second point. And the third point 120 and 90. and this is your third point. Then draw your straight line which passes through the 3 points, and again, since the soil is sand, the intercept on y-axis is equal to 0, so C is equal to 0. However, the value of y can be measured by your compass, or you can calculate the value of phi by taking the tan inverse of the slope of the straight line. Take any 2 points, maybe this point and this point. So the slope of this straight line is equal to 90 minus 60 over 120 minus 80. This is the slope. Take tan inverse of this slope on your calculator and you will find that phi is equal to 36.87 degrees.